Okay, so soon I'm going to be working on machine code generation for x64 machine code. But before I get into that, I thought I'd just read over some of the Intel Developers Manual. This is the combined volumes 1 to 4. So there's actually 10 volumes in here because 2 and 3 are split into A, B, C, and D. I'm obviously not going to read over the entire thing because it is 5,000 pages. But there are a few chapters that I want to focus on, so I'll have a look at chapter 1, just because it contains some information about notation and things like that. Chapter 2, I think we can mostly skip over, but I will read through and just see if there's anything interesting in there. The main information that I want to look at, though, is chapters 3 down to 7. There's probably some stuff in here that I'll skip over or just skim read. But this is basically the bulk of it. Chapter 8 onwards look interesting, but they're not really applicable to me right now because I'm only dealing with the integers. So just reading about the basic execution environment and things like that should be enough. I'll probably skip over chapter 5 because I think that's just literally just a list of instructions. And there are some appendices here, Appendix A to E. I don't know, maybe I'll skip over those as well, and then in another time I'll look at the volume 2 because that contains information on how to actually encode these instructions. So yeah, I think we'll just get into looking at chapter 1 to begin with. So let's skip to chapter 1. So there's a list of processes here that the manual covers. I think basically the point is that code written for all of these processes can run on other processes. They're backwards compatible. So even if you have code written for an older processor, it will still work on one of the newer ones. So notational conventions. This manual uses specific notation for data structure formats, for symbolic representation of instructions, and for hexadecimal and binary numbers. This notation is described below. So we have bit positions numbered from right to left, and addresses increase from bottom to top. The numerical value of a set bit is equal to 2 raised to the power of the bit position. So if bit 2 was set, that would be the value 2 to the power of 2, which is 4. So bit 0 would be 2 to the power of 0, which is 1, 2 to the power of 1, 2, so, normal binary counting. The bit offsets going from right to left means that we actually read these things in big endian, even though the processors are actually little endian machines. So this means that the bytes of a word are numbered starting from the least significant byte. Yeah, okay. Okay, so reserved bits and software compatibility. In many register and memory layout descriptions, certain bits are marked as reserved. When bits are marked as reserved, it's essential for compatibility with future processors that software treat these bits as having a future, though unknown, effect. The behavior of reserved bits should be regarded as not only undefined but unpredictable. So basically, just if something says it's reserved, just don't rely on it or use it in any way. Instruction operands. When instructions are represented symbolically, a subset of the IA32 assembly language is used. In this subset, an instruction has the following format. So we've got a label, which is followed by a colon. We've got a mnemonic, which describes the opcode, or the instruction, a class of instruction opcodes. And operands, argument 1, 2, and 3 are optional, so there can be from 0 to 3 operands depending on the opcode. So for example here we've got load reg, which is a label using the mov instruction, and the let's see, when two operands are present in an arithmetic or logical instruction, the right operand is the source and the left operand is the destination. So this is the same as a high-level language's assignment syntax. So for example here we've got EAX. So this would be the same as EAX equals subtotal. Where here it's going to copy the value of subtotal over to the EAX register. Hexadecimal and binary numbers. Hexadecimal numbers are represented by a string of hexadecimal digits followed by the character H. So for example 0F82EH. And then binary use B, but only in situations where there may be confusion as to the type of number. So I imagine, for example, if they've got the number 100, if they wanted to signify this was binary, they would put a B on the end. Segmented addressing, the processor uses byte addressing. This means memory is organized and accessed as a sequence of bytes. Whether one or more bytes are being accessed, a byte address is used to locate the byte or bytes memory. The range of memory that can be addressed is called an address space. The processor also supports segmented addressing. This is a form of addressing where a program may have many independent address spaces called segments. For example, the program can keep its code, instructions, and stack in separate segments. Code addresses would always refer to the code space, and stack addresses would always refer to the stack space. The following notation is used to specify a byte address within a segment. So we've got segment, followed by a colon, followed by a byte address. Yeah, so basically the byte address is an offset into the segment of memory pointed at by the DS register. So this is so DS is a segment register. CS, for example, the CS register points to the code segment, and the EIP register contains the address of the instruction. So I guess here basically we've got, you could have your address space here, and maybe the code segment starts here, and maybe the DS segment starts down here or something. So in this case, DS would point to this memory address as like a base, and in this case, the CS would point to this memory address as a base, and then if you wanted to address into them, so CS colon, 123 would basically point to here as a base and then add 123 as the offset into that code segment. Okay. A syntax for CPUID, CR, and MSR values. Obtain feature flag status and system information by using the CPUID instruction, by checking control register bits, and by reading model-specific registers. In my case, I'm actually on an AMD CPU on this computer, so I wouldn't even be able to use the model-specific registers from this manual anyway. I'd need to go and download the AMD manual for those. But CPUID will be important at some point, so we'll have a look at that. So basically this is the CPUID input and output. So if we're going to call the CPUID instruction, this is the input value for the EAX register. So EAX is basically going to be like an argument to CPUID. Then it defines the output register here. So this is EDX, and it shows us the flag or the information that we care about and which bit represents that information. So if we wanted to do this CPUID for SSE bit 25, we would basically mov EAX, and then we'd have like OX01 because this is 01H here. And then we would call CPUID. So EAX is basically like the argument for CPUID, and when CPUID executes, it's going to put its result into the EDX register, and we can inspect bit 25 to see whether it's on or off. We've got a similar thing for control registers and model-specific registers, but there's no EAX argument for them by the looks of it. So exceptions. An exception is an event that typically occurs when an instruction causes an error. For example, an attempt to divide by 0 generates an exception. However, some exceptions, such as breakpoints, occur under other conditions. Some types of exceptions may provide error codes. An error code reports additional information about the error. An example of the notation used to show an exception and an error code is shown below. So we've got the hash for an exception. PF, I guess, is this page fault here. And then the fault code is just the fault, the error information that's being reported. Under some conditions, exceptions that produce error codes may not be able to report an accurate code. In this case, the error code is 0, as shown below for the general protection exception. So we've got GP with 0. So now it's going on to related literature. We'll basically just skip over this. So we've got chapter 2, Intel 64 and IA32 architectures. We'll just skim over this chapter. You know, it's interesting, but you know, there's no need for us to read through all of this information. So let's see, is there anything useful here? So IA32 architecture family was preceded by 16-bit processors, the 8086 and 8088. Yep, okay, that's fine. So that's where segmentation was introduced. 286 is just some improvements to that. So 386 is where we got a 32-bit address bus that supports 4 gigabytes of physical memory. Let's see. We've got caches being introduced. Various improvements to internal data paths and things. P6, three-way superscalar. Let's see. Superscalar, I believe, is an architecture that can, on average, execute more than one instruction per clock cycle. So just lots of introduction of different instruction sets and extensions. So streaming SIMD extensions, SSE for example, will be very important later on. Let's see, just more improvements to, you know, we've got the support for hyperthreading technology and stuff. Okay, we'll just skip past these family descriptions. Let's see, what have we got? More on specific advances. So this is basically just describing the advances of the different families with some high-level diagrams. We won't worry too much about that. This is just a technical, more hardware information, but it's also at a high enough level that it's not really that useful to us, at least at this point anyway. Let's see, that architecture has changed quite a bit there by the looks of it, but again, high level diagram. Let's see, Sandy Bridge, Nehalem, Atom, SIMD instructions. This is interesting, but again, it's just more about when things were introduced, so we'll just skip over that stuff. So yeah, this is just a diagram of the register layouts and data types of SIMD extensions, so showing how that, for example, in a single 64-bit MMX register, you could pack 8 individual integers, or 4, or 2, or a single 64-bit, and then you can run instructions on these registers to do work in parallel. So this is basically instruction level parallelism. So there we've got MMX technology, SSSE3. Then we've got SSE to AVX, so that will include SSE 1 to, well, I guess 1 is just SSE, but 1, 2, 3, 4, I think there's a 4.1, I want to say, and a 4.2. And then there's AVX, which I believe there's AVX2, and there's also AVX 512, I want to say. But, again, so basically we've got, MMX registers for MMX instructions. SSE to AVX uses these XMM registers. I think AVX is using YMM, and then probably AVX 512 uses ZMM, if I'm remembering correctly. So anyway, we won't bother reading too much about that. Hyperthreading technology, though, could be interesting to read about. So Intel hyperthreading technology was developed to improve the performance of IA32 processors when executing multi-threaded operating system and application code or single-threaded applications under multitasking environments. The technology enables a single physical processor to execute 2 or more separate code streams, threads, concurrently using shared execution resources. So basically you can treat one core as if it were 2 logical processors. So if you have a CPU that has 4 physical cores with hyperthreading technology enabled, you can basically treat it as if you've got 8 logical cores. Intel HT technology is one form of hardware multi-threading capability in IA32 processor families. It differs from multiprocessor capability using separate, physically distinct packages within each physical processor package mated with a physical socket. Intel HT technology provides hardware multi-threading capability with a single physical package by using shared execution resources in a processor core. Architecturally, an IA32 processor that supports Intel HT technology consists of 2 or more logical processors, each of which has its own IA32 architectural state. Each logical processor consists of a full set of IA32 data registers, segment registers, control registers, debug registers, and most of the MSRs, MSR being a model-specific register. Each also has its own advanced programmable interrupt controller. Figure 2.5 shows a comparison of a processor that supports Intel HT technology and a traditional dual processor system. So here on the right we've got the traditional multiprocessor system where we have 2 cores, and the hyperthreading one basically has a single core with some shared execution resources. Unlike a traditional multiprocessor, I guess MP stands for multiprocessor, yeah, multiple processor system configuration that uses 2 or more separate physical IA32 processors, the logical processors in an IA32 processor supporting Intel HT technology share the core resources of a physical processor. This includes the execution engine and the system bus interface. After power-up and initialization, each logical processor can be independently directed and execute a specific thread interrupted or halted. Intel HT technology leverages the process and thread level parallelism found in contemporary operating systems and high-performance applications by providing 2 or more logical processors on a single chip. This configuration allows 2 or more threads. In the remainder of this document, the term thread will be used as a general term for the terms process and thread. Okay. To be executed simultaneously on each a physical processor. Each logical processor executes instructions from an application thread using the resources in the processor core. The core executes these threads concurrently using out-of-order instruction scheduling to maximize the use of execution units during each clock cycle. Okay, well, I think that's enough on that. Multi-core technology. Okay, well, I think we can skip over this as well. Intel 64 architecture, I'm maybe a bit more interested in because we're going to be writing the compiler to emit 64-bit code. So Intel 64 architecture increases the linear address space for software to 64 bits and supports physical address space up to 52 bits. This technology also introduces a new operating mode referred to as IA32E mode. IA32E mode operates in one of two submodes. Compatibility mode enables a 64-bit operating system to run most legacy 32-bit software unmodified. 64-bit mode enables 64-bit operating system to run applications written to access 64-bit address space. So that's what we're going to be doing. We'll be running in 64-bit sub-mode of IA32E. In the 64-bit mode, applications may access 64-bit flat linear addressing, 8 additional general-purpose registers, GPRs, 8 additional registers for streaming SIMD extensions, so that is SSE 1 through to 3. Is there not SSE 4? I don't know. 64-bit wide GPRs and instruction pointers, uniform byte register addressing, fast interrupt prioritizations mechanism, a new instruction pointer relative addressing mode, so I believe this is referring to RIP relative addressing, where you can basically take the instruction pointer RIP and you can add some 32-bit displacement to it, so you can address memory around the instruction pointer 2 gigabytes in either direction, so you can be more like position independent basically. Let's see. An Intel 64 architecture processor supports existing IA32 software because it is able to run all non-64-bit legacy modes supported by IA32 architecture. Most existing IA32 applications also run in compatibility mode. Virtualization technology I'm not actually interested in for the purpose of a compiler. So we'll just skip over the rest of this. This is just comparisons of different families and their sort of stats, I guess. Okay, lots of tables. Let's see, planned removal of Intel instruction set architecture features from upcoming products. I mean, I'm not going to worry about any of that. These ones have already been removed. Okay, basic execution environment, chapter 3. Okay. We'll try and read through all of this chapter. I'll basically skip anything that's about 16-bit and maybe some of the 32-bit stuff, but we'll see. So this chapter describes the basic execution environment of an Intel 64 or IA32 processor as seen by assembly language programmers. It describes how the processor executes instructions and how it stores and manipulates data. The execution environment described here includes memory, the address space, general purpose data registers, GPRs, segment registers, the flag register, and the instruction pointer register. So, modes of operation. The IA32 architecture supports 3 basic operating modes: protected mode, real address mode, and system management mode. The operating system determines which instructions and architectural features are accessible. So in protected mode, this is the native state of the processor. Among the capabilities of protected mode is the ability to directly execute real address mode 8086 software in protected multitasking environments. This feature is called virtual 8086 mode, although it's not actually a processor mode. Virtual 8086 mode is actually a protected mode attribute that can be enabled for any task. So basically this is a way, I guess, to run 16-bit code on the processor. Real address mode implements the programming environment of the Intel 8086 processor, so this is basically 16-bit code, and I believe because it's real address mode, we don't have any kind of virtual memory, I guess. System management mode. This provides an operating system or executive with transparent mechanism for implementing platform-specific functions such as power management and system security. I'm going to skip anything to do with that because I am not writing an operating system or executive. Okay, Intel 64 architecture. The Intel 64 architecture adds the IA32E mode. I assume that E here just means extended. So IA32E mode has two sub-modes, compatibility mode and 64-bit mode. Compatibility mode permits most legacy 16-bit and 32-bit applications to run without recompilation under a 64-bit operating system. So basically, in what is this? IA32E, we have compatibility mode, and within there, that will run, I assume, like a protected mode, where it could run code that was made for like IA32, which would be the 32-bit version of the architecture, and that could run in the virtual, what was it, virtual 8086 or something, which would basically allow this 16-bit and 32-bit applications. So 16-bit, I assume, would be running under this IA32E compatibility mode, where it's running in protected mode under virtual 8086. And for 32-bit code, it would be running under this IA32 protected mode or something. I'm sure I've probably mixed up some stuff there, but that's basically what it sounds like. Then we've got, let's see, compatibility mode is enabled by the operating system on a code segment basis. So basically, it sounds like the operating system can enable this for any program that's running. This means that a single 64-bit OS can support 64-bit applications running in 64-bit mode and support legacy 32-bit applications not recompiled for 64 bits running in compatibility mode. Compatibility mode is similar to the 32-bit protected mode. Oh, okay, so if compatibility mode just runs the 32-bit stuff directly, okay, I guess you can basically treat it like it's IA32. Compatibility mode uses 16-bit and 32-bit addresses and operand sizes. Like protected mode, this mode allows applications to access physical memory greater than 4 GB by using PAE, which is physical address extensions. So 64-bit mode, which is more what I'm interested in, this mode enables a 64-bit operating system to run applications written to access 64-bit linear address space. For brevity, the 64-bit submode is referred to as 64-bit mode in the IA32 architecture. 64-bit mode extends the number of general-purpose registers and SIMD extension registers from 8 to 16. General-purpose registers are widened to 64 bits. The mode also introduces a new opcode prefix REX to access the register extensions. 64-bit mode is enabled by the operating system on a code segment basis, again, just like the compatibility mode. Its default address size is 64 bits, and its default operand size is 32 bits. The default operand can be overridden on an instruction by instruction basis using a REX opcode prefix in conjunction with an operand size override prefix. Rex prefixes allow a 64-bit operand to be specified when operating in 64-bit mode. By using this mechanism, many existing instructions have been promoted to allow the use of 64-bit registers and 64-bit addresses. So basically, when we're programming in this mode, which we will be, 64-bit mode, if we did something like a mov to EAX, let's just say EBX, these operand sizes are 32-bit, which is the default operand size, but the address size is 64 bits. So if we were to do a calculation for an address size, that would be 64 bits, but the operand size by default is 32 bits. If we wanted to use a 64-bit operand like RAX and RBX, then we would need the Rex prefix to encode these instructions. So the instruction would get 1 byte longer, but we'd have access to those extended registers. So, yeah, I think that would be the case. So any program or task running on an IA32 processor is given a set of resources for executing instructions and for storing code data and state information. These resources make up the basic execution environment of an IA32 processor. So this is the 32-bit version of the execution environment. An Intel 64 processor supports the basic execution environment of an IA32 processor and a similar environment under IA32E mode that can execute 64-bit programs in the 64-bit submode and 32-bit programs in the compatibility submode. The basic execution environment is used jointly by the application programs and the operating system or executive running in the processor. So for the IA32, there is 4 gigabytes of address space because it's 2 to the 32 bits, and physical address space of up to 64 gigabytes. With that's 2 to the 36. I assume that's just because there's some extra addressing that can be done. Oh yeah, extended physical addressing in protected mode. For more information about addressing and address space greater than 4 gigabytes, we have to look at that section, which I'm not particularly interested in because we're not going to be doing 32 bits. Basic program execution registers. There are 8 general purpose registers, 6 segment registers, EFLAGs, and EIP. These are the basic execution environment in which to execute a set of general purpose instructions. These instructions perform basic integer arithmetic on byte, word, and double word integers, so byte being 8 bits, word being 16 bits, double word being 32 bits. Handle program flow control, operate on bit and byte strings, and address memory. X87 FPU registers, the 8 X87 FPU data registers, the X87 FPU control register, where FPU is floating point unit. Okay, basically this, I'm going to skip over this because I'm not going to use this. At least right now anyway. MMX registers is part of the SIMD, single instruction multiple data stuff. I believe that MMX is not worth using because we have access to SSE, which uses the XMM registers anyway, so we're just going to skip past this stuff. So here's a diagram of the execution environment. So this is everything that we've got access to technically as like an application programmer. So yeah, there's the general purpose registers, the address space, 0 up to 2 to the 32, 6 segment registers, flags, instruction pointer. The FPU has a, let's see, okay, so this has 8 registers that allow up to 80-bit floating point operations. And then we've got some SIMD stuff down here. XMM is 128 bits, MMX is 64 bits, and AVX, I think this was, AVX is 256-bit. So let's go to stack. To support procedure and subroutine calls and the passing of parameters between procedures or subroutines, a stack and stack management resources are included in the execution environment. The stack is located in memory. In addition to resources provided in the basic execution environment, the IA32 provides the following resources are part of its system-level architecture. They provide extensive support for operating system and system development software. Except for the I/O ports, the system resources are described in detail in the Intel 64 and IA32 architecture software developers manual volumes 3A, 3B, 3C, and 3D. So we're basically going to be skipping over all of this stuff because it doesn't seem relevant at all to me and writing a compiler. So 64-bit mode execution environment. The execution environment for 64-bit mode is similar to that described for the IA32 environment. So the difference is that the address space is now up to 2 to the 64 bytes, subject to canonical addressing requirement, so we'll have to pay attention to that. And physical address space of up to 2 to the 52 bytes. Software can query CPUID for the physical address size supported by a processor. Okay. Basic program execution registers. The GPRs available is 16 instead of 8. They're now 64 bits wide, so they can go up to quad word, which is 64 bits. Accessing byte registers is done uniformly to the lowest 8 bits. The instruction pointer register becomes 64 bits. EFLAGS is also extended to 64 bits and becomes RFLAGS, and the upper 32 bits of RFLAGS is reserved, so we should not rely or use those in any way at all. The stack pointer also goes to 64 bits, and it is not controlled by stack size is not controlled by a bit in the SS descriptor, as it is in non-64-bit modes, nor can pointer size be overridden by an instruction prefix. Okay. Descriptor table registers. The global descriptor table register GDTR and interrupt descriptor table register IDTR expand to 10 bytes so that they can hold a full 64-bit base address. The local descriptor table and the task register also expand to hold a full 64-bit address. So same diagram, it's been expanded to 64 bits basically, and we've got some more GPRs. Memory organization. The memory that the processor addresses on its bus is called physical memory. Physical memory is organized as a sequence of 8-bit bytes. Each byte is assigned a unique address called a physical address. The physical address space ranges from 0 to a maximum of 2 to the 36 minus 1, which is 64 gigabytes. So this is obviously for IA32. If the processor does not support Intel 64 architecture. Intel 64 architecture introduces a set of changes and in physical and linear address space. These are described in the other sections. Virtually any operating system or executive designed to work with an IA32 or Intel 64 processor will use the processor's memory management facilities to access memory. These facilities provide features such as segmentation and paging, which allow memory to be managed efficiently and reliably. Memory management is described in detail in Chapter 3, protected mode memory management, in Volume 3A, so we're not going to bother reading that. The following paragraphs describe the basic methods of addressing memory when memory management is used. Okay. IA32 memory models. When employing the processor's memory management facilities, programs do not do not directly address physical memory. Instead, they access memory using one of the three memory models, flat, segmented, or real address mode. Flat memory model appears to a program as a single continuous address space. This space is called linear address space. Code, data, and stacks are all contained in this address space. Linear address space is byte addressable with addresses running contiguously from 0 to 2 to the 32 minus 1, if not in the 64-bit mode. An address for any byte in the linear address space is called a linear address. Segmented memory model. Memory appears to a program as a group of independent address spaces called segments. Code, data, and stacks are typically contained in separate segments. To address a byte in a segment, a program issues a logical address. This consists of a segment selector and an offset. Logical addresses are often referred to as far pointers. The segment selector identifies the segment to be accessed, and the offset identifies a byte in the address space of the segment. Programs running on IA32 processor can address up to 16,000 segments of different sizes and types, and each segment can be as large as 2 to the 32 bytes. Internally, all the segments that are defined for a system are mapped into the processor's linear address space. To access a memory location, the processor thus translates each logical address into a linear address. This translation is transparent to the application program. The primary reason for using segmented memory is to increase the reliability of programs and systems. For example, placing a program stack in a separate segment prevents the stack from growing into the code or data space and overwriting instructions or data respectively. Real address mode memory model is for the 8086 processor. It's supported to provide compatibility with existing programs written to run on the 8086. And yeah, it's basically 16-bit stuff here, so we've got some diagrams of the different models. Flat memory model is sort of what we expect now. It's just, you've got some memory and you can address it directly in it. Segmented is what we went over earlier, and real address mode is just, we're not even going to look at that. Paging and virtual memory. With the flat or segmented memory model, linear address space is mapped into the processor's physical address space either directly or through paging. When using direct mapping, paging disabled, each linear address has a one-to-one correspondence with a physical address. Linear addresses are sent out on the processor's address lines without any translation. When using the IA32 architecture's paging mechanism, paging enabled, linear address space is divided up into pages which are mapped to virtual memory. The pages of virtual memory are then mapped as needed into physical memory, and when an operating system or executive uses paging, the paging mechanism is transparent to an application program. All that the application sees is linear address space. In addition to IA32 architecture's paging mechanism includes extensions that support physical address extensions, PAE, to address physical address space greater than 4 gigabytes, page size extensions to map linear address to physical address in 4 megabyte pages, because I believe I saw it when skimming through that history chapter. One of the processors introduced a hard-coded 4 kilobytes of page size. So I guess this PSE is basically you can increase it to a larger page size. So memory organization in 64-bit mode. So obviously the physical address space is greater than 64 gigabytes. The actual physical address size of IA32 processors is implementation specific. In 64-bit mode, there is architectural support for 64-bit linear address space. However, processors supporting Intel 64 architecture may implement less than 64 bits. The linear address space is mapped into the processor physical address space through the PAE paging mechanism. Okay. When writing code for an IA32 or Intel 64 processor, a programmer needs to know the operating mode the processor is going to be in when executing the code and the memory model being used. The relationship between operating modes and memory modes is as follows. Protected mode. When in protected mode, the processor can use any of the memory models described in this section. The memory model used depends on the design of the operating system or executive. Okay, that's fine. Real address mode, don't care. System management mode, don't care. Compatibility mode, software that needs to run in compatibility mode should observe the same memory model as those targeted to run in 32-bit protected mode. The effect of segmentation is the same as 32-bit mode. 64-bit mode, segmentation is generally but not completely disabled, creating a flat 64-bit linear address space. Specifically, the processor treats the segments CS, DS, ES, and SS as 0 in 64-bit mode. This makes the linear address equal an effective address. Segmented and real address modes are not available in 64-bit mode. So I guess that basically means that if we had 32 IA32 protected mode or something, you could say, for example, like here's the CS segment, and I'm going to go into some offset from there. In 64-bit mode, this is now equal to 0, along with all of the other ones, DS, ES, and SS, so they all point to the bottom. So they're all effectively just using the same same addresses of memory. So any calculation of an address from any of these segments is basically just, you can just cancel these out because there's just 0. 32-bit and 16-bit address and operand sizes. IA32 processors in protected mode can be configured for 32-bit or 16-bit addresses and operand sizes. With 32-bit addresses and operand sizes, the maximum linear address is this. Okay, yep, that's fine. Yep. When using 32-bit addressing, a logical address or far pointer consists of 16-bit segment selector and a 32-bit offset. When using 16-bit addressing, an address consists of a 16-bit segment selector and a 16-bit offset. Instruction prefixes allow temporary overrides of the default address and/or operand sizes from within a program. When operating in protected mode, the segment descriptor for the currently executing code segment defines the default address and operand size. A segment descriptor is a system data structure not normally visible to application code. Assembly directives allow the default addressing mode and operand size to be chosen for a program. The assembler and other tools then set up the segment descriptor for the code segment appropriately. When operating in real address mode, the default addressing and operand size is 16 bits. An address size override can be used in real address modes to enable 32-bit addressing. However, the maximum allowable 32-bit linear address is still the same as it was up here, I think. Oh no, it's got to the 20. Extended physical addressing in protected mode. Beginning with the P6 family processors, the IA32 architecture supports addressing of up to 64 gigabytes, 2 to 36 bytes of physical memory. A program or task could not address locations in this address space directly. Instead, it addressed individual linear address spaces of up to 4 gigabytes that mapped to 64 gigabytes physical address space through a virtual memory management mechanism. Using this mechanism, an operating system can enable a program to switch 4 gigabyte linear address spaces with 64 gigabyte physical address space. The use of extended physical addressing requires the processor to operate in protected mode and the operating system to provide a virtual memory management system. Okay, let's go down to the 64-bit mode section. In most cases, 64-bit mode uses flat address space for code, data, and stacks. In 64-bit mode, that if there is no address size override, the size of effective address calculations is 64 bits. An effective address calculation uses 64-bit base and index registers and sign extend displacements to 64 bits. Okay, in the flat address space of 64-bit mode, linear addresses are equal to effective addresses because the base address is 0. In the event that FS or GS segments are used with a non-zero base, this rule does not hold. So I guess there are 2 more segments, because there are 6 segment registers. FS and GS are not set to 0, so these could be anything. I believe these tend to be used by operating systems to provide functionality for like thread local storage and thread metadata and stuff. So I'm just going to treat these 2 as basically being reserved by the operating system. In 64-bit mode, the effective address components are added and the effective address is truncated before adding the full 64-bit segment base. The base is never truncated regardless of addressing mode in 64-bit mode. The instruction pointer is extended to 64 bits and it's now called RIP, right? So we've got, IP is the 16-bit, 32-bit is the EIP, and then 64-bit is RIP. 32-bit gets 0 extension, whereas 16-bit gets not modified. Okay. Generally, displacements and immediates in 64-bit mode are not extended to 64 bits. They are still limited to 32 bits and sign extended during effective address calculations. In 64-bit mode, however, support is provided for 64-bit displacement and immediate forms of the MOV instruction. All 16-bit and 32-bit address calculations are 0 extended in IA32E mode to form 64-bit addresses. Address calculations are first truncated to the effective address size of the current mode, as overridden by any address size prefix. The result is then 0 extended to the full 64-bit address width. Because of this, 16-bit and 32-bit applications running compatibility mode can access only the low 4 gigabytes of the 64-bit mode effective addresses. Likewise, a 32-bit address generated in 64-bit mode can access only the low 4 gigabytes of the 64-bit mode effective addresses. Okay, so basically, if we use 32-bit, yeah, okay, so the result is then 0 extended. Yeah, okay, well we're gonna be using 64-bit address sizes, so I think we don't need to worry too much about those things happening. Canonical addressing, so this is where the limitation of addressing comes in. In 64-bit mode, an address is considered to be in canonical form if address bit 63 to the most significant bit implemented by the microarchitecture are set to either all ones or all zeros. Intel 64 architecture defines 64-bit linear address. Implementations can support less. The first implementation of IA32 processors with Intel 64 architecture supports a 48-bit linear address. This means a canonical address must have bits 63 through 48 set to zeros or ones depending on whether bit 47 is a 0 or 1. So if we looked at any memory addresses in 64-bit code, we should see those top bits either all zeros or all ones, so that they're in canonical form. Although implementations may not use all 64 bits of the linear address, they should check bits 63 to the most significant bit implemented to see if the address is in canonical form. If a linear address reference is not in canonical form, the implementation should generate an exception. In most cases, a general protection exception is generated. However, in the case of explicit or implicit stack references, a stack fault is generated. Instructions that have implied stack references, by default the SS segment register, you use the SS segment register. So these include push-pop related instructions and instructions using RSP or RBP as base registers. In these cases, the canonical fault is SS, but also in 64-bit mode, SS is going to be 0, so that's not going to change the actual address calculated. But if they do use this implicitly, then we would get an SS exception. If an instruction uses base registers RSP, RBP, and uses segment override prefix to specify a non-SS segment, a canonical fault generates a GP instead of an SS. In 64-bit mode, only FS and GS segment overrides are applicable in this situation, because those are the exceptions to not being disabled. Other segment override prefixes, CS, DS, ES, and SS are ignored. Note that this also means that an SS segment override applied to a non-stack register reference is also ignored. Such a sequence still produces a GP for a canonical fault and not SS. So basic execution registers. Let's see, we've got general purpose registers. There are 8 of them. So this is AX, BX, CX, DX, SI, DI, BP, and SP. So the way we'll remember this is just A, B, C, D. Then we've got source index, destination index, base pointer, and stack pointer. Registers, there are 6 segment registers. So that was CS, DS, ES, SS, FS, and GS. And then we've got a flags register and an instruction pointer register. So these are used for operands for logical and arithmetic operations, operands for address calculations and memory pointers. Although all of these registers are available for general storage of operands, results, and pointers, caution should be used when referencing the ESP register. The ESP register holds the stack pointer and as a general rule should not be used for any other purpose. Many instructions assign specific registers to hold operands. For example, string instructions use the contents of ECX, ESI, and EDI registers as operands. When using a segmented memory model, some instructions assume that pointers in certain registers are relative to specific segments. Okay, well, I'm not going to worry about the segments. The special uses of general purpose registers by instructions are described in chapter 5, which I'll probably mostly be skipping because we'll see those in the references in volume 2 when we're actually encoding instructions anyway. The following is a summary of special uses. AX is accumulator for operands and results data, BX is pointer for data into DS segments, CX counter for string and loop operations, EDX is IO pointer. SI is a source pointer, then we've got DI, which is a destination pointer, ESP is the stack pointer, and then BP is the pointer to data on the stack. This is the base pointer. The lower 16 bits of the general purpose registers map directly to the register set found in the 8086 and Intel 286 processors and can be referenced with the names AX, BX, CX, DX, BP, SI, DI, and SP. Each of the lower 2 bytes of the A, B, C, and D registers can be referenced by the names AH through to DH for the high bytes. So that's these ones here, and AL to DL for the low bytes here, and that only applies to A, B, C, and D. None of the other registers get that split. Okay, so general purpose registers in 64-bit mode. So basically they've been expanded to work with either 32-bit or 64-bit operands. If a 32-bit operand size is specified, then you can basically refer to them in assembly with these E prefixed names. And for the extended ones, it's R8D to R15D, where D is equal to double, which is equal to 32 bits. If a 64-bit operand is specified, then it's RAX through to RSP, and then we have R8 to R15 with no suffix. So these are the 8 new, so R8 to 15 are the new general purpose registers. All of these registers can be accessed at a byte, word, D word, and Q word level, so 8 bits, 16 bits, 32 bits, and 64 bits. Rex prefixes are used to generate 64-bit operand sizes or to reference the extended registers. So if we want to access R8 to 15, we have to use a Rex prefix in the instruction encoding. And if we want to use a 64-bit operand, we also have to use a Rex prefix. Registers only available in 64-bit mode, which is the extended ones, and it looks like we also get extended XMM to XMM15, which we won't be using because those will be floating point and SIMD, are preserved across transitions from 64-bit mode into compatibility mode. I won't worry about that. Then what we've got here, we've got in 64-bit mode, there are limitations on accessing byte registers, so that would be these AL to AH ones. An instruction cannot reference legacy high bytes, for example, AH, DH, CH, DH, and one of the new byte registers at the same time. For example, the low byte of the R8X register. However, instructions may reference low bytes and new byte registers at the same time. The architecture enforces this limitation by changing the high byte references to low byte references of the other 4 registers. Okay, so basically, if we want to use any of these registers here to access a high byte, we can only use them with other registers that don't have a Rex prefix. If we use a Rex prefix, then these are not available anymore. These are actually replaced with the low bytes of the other 4 registers. So in the compiler, we'll have to check, we'll have to say, if we have a Rex prefix, then this is not allowed. Let's see, when in 64-bit mode, operand size determines the number of valid bits in the destination. 64-bit operands generate 64-bit result in the destination general purpose register. 32-bit operands generate a 32-bit result. 0 extended 64-bit results in the destination general purpose register. So this is basically where stuff comes from, like if you say mov EAX and then you move something else in there, we'll say EBX. This will copy all of the 32 bits over, and then the top 32 bits get zeroed out. 8 and 16 bits, the upper bits are not modified, so this 0 extension only applies to 32-bit operands. So, segment registers, CS, DS, SS, ES, FS, and GS hold 16-bit segment selectors. A segment selector is a special pointer that identifies a segment in memory. To access a particular segment in memory, the segment selector for that segment must be present in the appropriate segment register. When writing application code, programmers generally create segments with assembly directives. I think I'm not going to worry about this because that seems like a 32-bit IA32 problem. How they're used depends on the memory model. Let's see, typically 2 overlapping. Yeah, okay, that's fine. We'll skip this bit. Each of the segments is associated with three types of storage: code, data, or stack. CS contains the code segment, which is where EIP is related to. DS, ES, FS, and GS are data segments. And then SS is a stack segment. So implicit segments and things like that could make sense with either one of these storage areas. Let's see. Yeah, not going to worry about that. Segment registers in 64-bit mode. CS, DS, ES, and SS are treated as if each segment base is 0, regardless of the value associated with the segment descriptor base. This creates a flat address space for code, data, and stack. FS and GS are exceptions. Both segment registers may be used as additional base registers in linear address calculations. In the addressing of local data by certain operating system data structures. So this is where FS and GS will be used for things like thread local storage. Even though segmentation is generally disabled, segment register loads may cause processor to perform segment access assists. Such checks are needed because this segment register loaded in 64-bit mode may be used by an application running in compatibility mode. Okay. So flags, basically this is just describing different flag bits being reserved and stuff. Cannot be modified directly, can be modified directly using special purpose instructions. There are no instructions that allow the whole register to be examined or modified directly. The following instructions can be used to move groups of flags to and from the procedure stack or the EAX register. So there are just different ways to access flags, and something about task state. We're not going to worry about that. Diagram of flags and which ones are reserved. These status flags in the flag register can be useful to know, but we're going to skip over that for now. DF flag controls the direction of string instructions. System flags, okay, we're not going to worry about that. R flags, so E flags is extended to 64 bits and called R flags. The upper 32 bits is reserved. Okay, instruction pointer. So the instruction pointer register contains the offset in the current code segment to the next instruction to be executed. It's advanced from one instruction boundary to the next in straight line code, or it's moved ahead or backwards by a number of instructions when executing jump by condition, call, ret, and iret instructions. The EIP register cannot be accessed directly by software. It's controlled implicitly by control transfer instructions such as jump, call, ret, interrupts, and exceptions. The only way to read the EIP register is to execute a call instruction and then read the value of the return instruction pointer from the procedure stack. So when you call, the processor will push the return address onto the stack, and you can read the address from the stack. The EIP can be loaded indirectly by modifying the return instruction pointer on the stack and executing a return. So when we return, it's going to read the address on the stack and jump back to that point. All IA32 processors prefetch instructions. Because of instruction prefetching, an instruction address read from the bus during an instruction load does not match the value of the EIP register, even though different processors... Okay, yeah, we're just going to skip that. Instruction pointer in 64-bit mode. So basically it becomes RIP instead of EIP, and it's extended to 64-bit offsets to the next instruction. It also supports a technique called RIP relative addressing, which is where you can add a displacement to the instruction pointer to address relative to the instruction pointer. Okay, operand size and address size attributes. When the processor is executing in protected mode, every code segment has a default operand size attribute and address size attribute. These attributes are selected with the D default size flag in the segment descriptor for the code segment. When the D flag is set, the 32-bit operand size And address size attributes are selected. When it's clear, then 16-bit size attributes are selected. Okay, the operand size selects. Okay, I'm going to skip this stuff because this is obviously IA32. Operand size and address size in 64-bit mode. In 64-bit mode, the default address size is 64 bits, as you'd expect, and the default operand size is 32 bits, which we've already seen. Address size and operand size prefixes allow the mixing of 32 and 64-bit data and 32 and 64-bit addresses. They can be overridden on an instruction-by-instruction basis using a 66H instruction prefix and the rex.w prefix. Rex prefixes consist of 4-bit fields that form 16 different values. The W-bit field is referred to as rex.w. If W field is properly set, the prefix specifies an operand size override to 64 bits. I assume W must mean like wide or something. Note that software can still use the operand size 66 prefix to toggle to 16-bit operand size. However, setting the rex.w takes precedence over the operand size prefix 66 when both are used. So if we set both the rex.w for 64-bit and we include a 66 prefix for 16-bit, the W prefix will win out and we'll get 64 bits. So in this table here, we've got, this is the default, where by default in 64-bit mode, we have 64-bit addresses, but 32-bit operands. If we wanted to change it to using 32-bit addresses for some reason, then we would use the address size prefix 67 to override that. If we wanted to have 16-bit operands, so if we wanted to do like a mov into AX, for example, this is a 16-bit operand, so we would have to set the 66 prefix. If we wanted to use 64-bit operands, so for example RAX, then we would need to set the rex.w prefix bit. And if we set both of them, so if both rex.w and 66 are set, then we'll actually get the operand size 64 because the rex.w takes precedent. So operand addressing, IA32 machine instructions act on 0 or more operands. Some operands are specified explicitly and others are implicit. The data for a source operand can be located in the instruction itself, which is called an immediate operand, a register, a memory location, an I/O port. And the destination can be returned to a register, a memory location, and an I/O port. So a destination can't be an immediate, basically. Immediate operands. Some instructions use data encoded in the instruction itself as the source operand. These operands are called immediate operands or simply immediates. For example, the following add instruction adds an immediate value of 14 to the contents of the EAX register. So here the literal is hard-coded as a direct immediate value within the instruction itself. All arithmetic instructions allow the source operand to be immediate, except for the div and idiv instructions. The maximum value allowed for an immediate varies among instructions, but can never be greater than the maximum value of an unsigned double word integer, except, as we saw earlier, the mov instruction has an exception where it can take a 64-bit immediate. So register operands, we've basically got 32-bit registers, so we've seen all these before. 16-bit is referred to without the E. and then 8-bit is the high byte and the low bytes. Segment registers, okay, yeah, that all seems fine. Let's see, what have we got here? More just the same stuff, but 64 bits. Okay, there was a little bit up here though. Some instructions, such as div and mul instructions, use quad word operands contained of a pair of 32-bit registers. Register pairs are represented with a colon separating them. For example, in the register pair EDX colon EAX, EDX contains the high order bits and EAX contains the low order bits of a quad word operand. So I think in the 64-bit case, it changes to a 128-bit operand, so this would be a double quad word, or I've seen it called an oct word as well. So that would be the same thing, just using R instead. So memory operands, source and destination operands in memory are referenced by means of a segment selector and an offset. Segment selectors specify the segment containing the operand. Offsets specify the linear or effective address of the operand. Offsets can be 32 bits or 16 bits, and in 64-bit mode, it's the same thing, but it's just, allows up to 64 bits. Specifying a segment selector, so it can be done implicitly or explicitly. The common method is specifying a selector is to load it into a segment register and then allow the processor to select the register implicitly, depending on the type of operation being performed. The processor automatically chooses a segment according to the rules in the next table. So instructions will automatically assume CS, the stack instructions, so pushes and pops and stuff assume SS. Local data is DS and destination strings is ES. None of these matter really in 64-bit mode because they're all set to 0. So segmentation in 64-bit mode, the effects of segmentation depend on whether the processor is running in compatibility mode or 64-bit mode. In compatibility mode, it's the same as IA32 mode. In 64-bit mode, segmentation is generally but not completely disabled, creating a flat 64-bit linear address space. The processor treats the segment base of CS, DS, ES, and SS as 0, creating a linear address that is equal to the effective address. Because being 0, we're not gonna, change the offset of the starting point in memory, so they're all the same. Specifying an offset. The offset part of a memory address can be specified directly as a static value called a displacement, or through an address computation made up of one or more of the following components. So we have a displacement, which can be an 8, 16, or 32-bit value, a base, which is a general purpose register, an index, which is another general purpose register, and then a scale, 2, 4, or 8, which is multiplied by the index value. The offset, which results from adding these components, is called an effective address. Each of these components can have either a positive or negative 2's complement value, with the exception of the scaling factor. So basically it's calculated in this way. We have the base plus the index multiplied by the scale plus the displacement. The uses of general purpose registers as base or index components are restricted in the following manner. So the SP register can't be used as an index, and when SP or BP is used as the base, the SS segment is the default. In 64-bit, that doesn't make any difference. So in 64-bit mode, the only restriction we have to pay attention to here is that the SP register can't be used as an index. Okay, so we've got some Rex stuff to look out for. We've got some canonical address stuff to look out for, and we've got the SP can't be used as index to look out for as well. The base, index, and displacement components can be used in any combination, and any of these components can be null. A scale factor may only be used when an index is also used, because it wouldn't make sense to scale nothing. Each possible combination is useful for data structures commonly used by programmers in high-level languages and assembly. Yeah, so for example, you could use the base as a way to get to like the start of a struct, and then you could use a displacement or something to go and get a field from the struct. And index, if you happen to be able to scale by 2, 4, or 8, you could use that to go into like arrays and things. So specifying an offset in 64-bit mode, the displacement is still only up to 32-bit, and we get the additional addressing of RIP relative. So RIP relative addressing uses assigned 32-bit displacement to calculate the effective address of the next instruction by sign extend the 32-bit value and add to the 64-bit value in RIP. So basically we can say the instruction pointer plus some 32-bit signed integer, so we can go 2 gigabytes either way of the instruction pointer. Assembler and compiler addressing modes, not going to worry about. IO port addressing, not even going to worry about IO ports. So we've got data types here. Let's just skim through this quickly. Fundamental data types. I mean, we pretty much know what all this stuff is. Let's see, alignment. Words, double words, and quad words do not need to be aligned in memory on natural boundaries. The natural boundaries for words, double words, and quad words are even numbered addresses, addresses evenly divisible by 4, and addresses evenly divisible by 8, respectively. However, to improve performance of programs, data structures, especially stacks, should be aligned on natural boundaries whenever possible. The reason for this is that the processor requires 2 memory accesses to make an unaligned memory access. Aligned accesses require only 1 memory access. A word or double word operand that crosses a 4-byte boundary, or a word or a quad word operand that crosses a 8-byte boundary is considered unaligned and requires 2 separate memory bus cycles for access. Some instructions that operate on double quad words require memory operands to be aligned on a natural boundary. These instructions generate a general protection exception if unaligned operand is specified. Okay. A natural boundary for a double quad word is any address evenly divisible by 16. Other instructions that operate on double quad words permit unaligned access. However, additional memory bus cycles are required to access unaligned data from memory. Okay. I feel like I should start writing a few of these things down before I forget about them. So before I continue on, I think so far we've basically got canonical address checks that we have to look out for. Rex prefix prohibits use of AH to DH. We've got basically align data, align data on the stack. Let's say to, I don't know, it's either going to be 8 or 16 byte alignment. Maybe if we're expecting SIMD, we should stick with 16 byte alignment. Okay, and I think there was one more thing, but I'll write it down when I remember it. Okay, before I go on, let me just skim up a little bit more, just to make sure that I haven't missed too much. Canonical addressing, okay. Alright, let's just carry on then. Right, so that was alignment. Numeric data types, yeah, okay, this is just integers and unsigned integers. Floating point I'm going to skip for now. pointer data types in 64-bit mode. In 64-bit mode, a near pointer is 64 bits. This equates to an effective address. Far pointers in 64-bit mode can be one of three forms. So basically a segment selector with some offset is a far pointer bit field. SIMD, strings, okay, we'll skip over those for now. More floating point stuff. Yep, we'll skip over all this floating point stuff for now. We're only using integers to begin with. Okay, instruction set summary. Is there anything useful in here right now? I think that this is just... It's basically just a list of instructions, so I'm going to skip past this. We'll go to procedure calls and interrupts and exceptions. So this chapter describes the facilities in the Intel 64 and IA32 architectures for executing calls to procedures or subroutines. It also describes how interrupts and exceptions are handled from the perspective of an application programmer. So we've got call and ret and enter and leave. Now, I know that I'm going to ignore enter and leave. We're just going to stick with call and ret. So I'm going to skip anything related to these. Both of these procedure call mechanisms use the procedure stack, commonly referred to as simply the stack, to save the state of the calling procedure, pass parameters to the call procedure, and store local variables for the currently executing procedure. The processor's facilities for handling interrupts and exceptions are similar to those used by the call and ret instructions. Processors that support control flow enforcement technology support an additional stack referred to as the shadow stack. The call instruction, when shadow stacks are enabled, additionally saves the state of the calling procedure on the shadow stack, and the ret instruction restores the state of the calling procedure if the state on the stack and the shadow stack match. So if they don't match, what does that do? Does that generate an exception? Well, anyway, stacks. The stack is a contiguous array of memory locations. It's contained in a segment identified by the segment selector in the SS register. When using a flat memory model, the stack can be located anywhere in the linear address space for the program. A stack can be up to 4 GB long, the maximum size of a segment, but that's for IA32. Items are placed on the stack using a push instruction and removed using a pop instruction. When an item is pushed onto the stack, the processor decrements ESP register and then writes the item at the new top of the stack. When the item is popped off the stack, the processor reads the item from the top of the stack, then increments the ESP register. In this manner, the stack grows down in memory towards lesser addresses when items are pushed on the stack, and shrinks up towards greater addresses when items are popped from the stack. A program or operating system executive can set up many stacks. When a system sets up many stacks, only one stack, the current stack, is available at a time. The current stack is the one contained in the segment referenced by the SS register. Setting up a stack, we're not going to worry about that. Stack alignment. The stack pointer for a stack segment should be aligned on a 16-bit word or 32-bit double word boundaries, depending on the width of the stack segment. The D flag in the segment descriptor for the current code segment sets the stack segment width. Okay, the push and pop instructions use the D flag to determine how much to increment or decrement the stack pointer when in a push or pop operation. When the stack width is 16 bits, the stack pointer is incremented or decremented in 16-bit increments. Okay, so I assume that in 64 bits, that will just change to being 8 bytes instead of 2 or 4 bytes. Okay, one exception to this rule, don't need to worry about that. The processor does not check stack pointer alignment. It is the responsibility of the programs, tasks, and system procedures running on the processor to maintain proper alignment of stack pointers. Misaligning a stack pointer can cause serious performance degradation and, in some instances, program failures. So basically, yeah, keep the stack aligned. Address size attributes for stack accesses. Yeah, okay, well that's just sounds like IA32 stuff. Procedure linking information. This is just going over how to use the stack pointer and the base pointer, which I'm not going to worry about too much. Prior to branching to the first instruction of a called procedure, the call instruction pushes the address in the EIP register onto the current stack. This address is then called the return instruction pointer, and it points to the instruction where execution of the calling procedure should resume following a return from the called procedure. Upon returning from a called procedure, the ret instruction pops the return instruction pointer from the stack back into the EIP register. Execution of the calling procedure then resumes. The processor does not keep track of the location of the return instruction pointer. It's thus up to the programmer to ensure that stack pointer is pointing to the return instruction pointer on the stack prior to issuing a ret instruction. A common way to reset the stack pointer to point to the return instruction pointer is to move the contents of the EBP register into the ESP register. If the EBP register is loaded with the stack pointer immediately following a procedure call, it should point to the return instruction pointer on the stack. The processor does not require that the return instruction pointer point back to the calling procedure. Prior to executing the ret instruction, the return instruction pointer can be manipulated in software to point to any address in the code segment. Or any other code segment, which would be a far return, so near return, far return. Performing such an operation, however, should be undertaken very cautiously, using only well-defined code entry points. So in 64-bit mode, address calculations that reference SS are treated as if the segment base is 0. Yeah, that's all. We've heard all of this before. Push and pop are 64 bits. Yep, that's what we expected. Shadow stacks. So a shadow stack is a second stack used exclusively for control transfer operations. This stack is separate from the procedure stack. The shadow stack is not used to store data, hence is not explicitly writable by software. Writes to the shadow stack are restricted to control transfer instructions and shadow stack management instructions. Shadow stacks can be enabled separately for privilege level 3 user mode or privilege levels less than 3 supervisor mode. Shadow stacks are active only in protected mode with paging enabled. Shadow stacks cannot be enabled for programs executing in virtual x86 mode. Processors that support shadow stacks have an architectural register called shadow stack pointer that points to the top of the shadow stack. SSP cannot be directly encoded as a source, destination, or memory operand in instructions. The width of the shadow stack is 32-bit in 32-bit in compatibility mode and 64-bit in 64-bit mode. The address size attribute of the shadow stack is likewise 32-bit in... Oh, okay, yep. The size of the shadow stack pushes and pops for a far call and call to interrupt exception handlers is fixed at 64 bits and the processor uses 8-bit. Okay. So shadow stack then, that was a control flow enforcement technology. Control flow enforcement technology, Windows. Let's see. Yeah, I wonder. how do we, let's see, Windows 11 shadow stack. Device security. Then we've got core isolation details. Memory integrity. Oh, okay, so there's two different ones. Virtualization-based security. And this one is, okay, hardware enforced stack protection, kernel mode hardware enforced stack protection. Okay, so this one is off by default, and this one is on by default. I don't quite know the difference between those two, but this sounds like the shadow stack, whether you enable the shadow stack or not. So, I don't know. It was worth having a look at. Okay. Calling procedures using colon ret. The call instruction allows control transfers to procedures within the current code segment, which is a near call, and a different code segment, which is a far call. Okay, that's fine. Don't need that. Okay, the rets instruction is also near and far. Okay, so I think the only thing to keep in mind here is basically near and far. We probably just want to use near calls and near returns when encoding. This is just what steps they take, so we won't worry about this. We won't worry about parameters. Calls to other privilege levels. Yeah, I'm not going to worry about that stuff. Okay, I think I can basically skip over these things. Branch functions, yep, I'm not going to worry about those. Interrupts and exceptions, I'm not going to worry about either. Yep, okay, more interrupt stuff. Procedure calls for block structured languages. That's enter and leave, so I'm just going to ignore those. Anything else in here? Okay, we're on to chapter 7. I'll have a read through this chapter and then I think I'll stop there. So general purpose instructions are a subset of the IA32 instructions that represent the fundamental instruction set for Intel IA32 processors. These instructions were introduced in the IA32 architecture. With the first IA32 processors, additional instructions were added. Intel 64 extends the capability of most general purpose instructions, so they're able to handle 64-bit data in 64-bit mode. A small number of general purpose instructions are not supported in 64-bit mode. Okay, so programming environment for GP instructions. This is 32-bit stuff. It's all the stuff we've seen before. 64-bit mode. You know, again, all of the stuff that we've seen before with the registers and 64 bits and everything. Near and far pointers, bit fields, etc., etc. So, data transfer instructions move bytes, words, double words, and quad words between memory and the processor's registers and between registers. For the purpose of this discussion, these instructions are divided into subordinate subgroups that provide for general data movement exchange, stack manipulation, and type conversion. So, MOV and CMOV, conditional move, instructions transfer data between memory and registers, or between registers. So no memory to memory. It handles data transfers along the paths listed in table 7.1. MOV instruction cannot move data from one memory location to another, or from one segment register to another segment register. Memory to memory moves are performed with the MOV-S instruction. Conditional moves check the state of the status flags and basically do the copy based on that. So, yeah, okay. Mnemonics for CMOV CC are the conditions, so we can have CMOV above or CMOV not below equal. There are alternative names for the same instruction. CMOV CC instructions are useful for optimizing small if constructions. They also help eliminate branching overhead for if statements and the possibility of branch mispredictions by the processor. These conditional move instructions are supported in the P6 family. Okay, I'll just assume that they're supported for anything I'm going to be writing code for. Exchange instructions swap the contents of one or more operands and in some cases perform additional operations, such as asserting the lock signal or modifying flags in the eFlags register. The exchange instruction swaps the contents of two operands. This instruction takes the place of three MOV instructions and does not require a temporary location to save the contents of one operand location while the other is being loaded. When a memory operand is used with the exchange instruction, the processor's lock signal is automatically asserted. This instruction is thus useful for implementing semaphores or similar data structures for process synchronization. See bus locking in volume 3 for bus locking. B-swap is byte swap, reverses the order in 32-bit register operand. So I guess this would be useful for something like converting endianness. Executing this instruction twice in a row leaves the register with the same value as before. The B-swap instruction is useful for converting between big endian and little endian data formats. This instruction also speeds execution of decimal arithmetic. Okay. Xadd is exchange and add, swaps two operands and then stores the sum of the two operands. Okay. Compare exchange. Yep. Okay, compare exchange. Synchronize operations in systems that use multiple processors. Okay. Commonly used for testing and modifying semaphores. Exchange instructions in 64-bit. Compare exchange 16B is available in 64-bit only. It's an extension of the functionality provided. Okay. Stack manipulation instructions, push pop, push A, push A and pop A, you do all the registers. Instructions move data to and from the stack. The push instruction decrements. Okay, I mean, yeah, I think maybe I don't need to go through this whole chapter then. We'll just skip through and see if there's anything else useful that comes up. Let's see, simple conversion, so there's convert byte to word, and I guess these will do things like sign extension and or not sign extension, so move with sign or zero extension, MOV SX, MOV ZX, binary arithmetic, comparison, yeah, okay, this is all just, okay. Alright, I think that I will be able to just skip this chapter then, because this is just about, you know, how do you basically program assembly. Maybe we'll come back to this chapter a bit later if we need to know some more details, but yeah, I mean, that was a pretty short chapter. Then on to chapter 8, so this one isn't useful for me in the context of the compiler right now. Okay, well, I guess I'll leave it there. Next time I'm going to move on to volume 2 and read about the instruction encoding and formats, and then start actually generating some machine code.